Hi, my name is Guillermo Fernandez, and today I'll be talking about Mariotte bottle experiment 2. The goal of this experiment was to calculate an estimated value for gravity. This was achieved by analyzing the function of the Mariotte bottle. To calculate the value for gravity, we used the method of least squares. In this work, the value for gravity obtained was that of 0.15 plus minus 0.13 meters per second squared. We found out that our results were inconclusive, since the expected value is far from the uncertainty of the measurements. The fundamentals behind the Mariotte bottle were explained in the first report. In this report, we will analyze the average velocity of effusion within Mariotte's bottle by measuring the water level height over time. To do this, the height h must be a variable. 5 different heights will be considered and the behavior will be analyzed in each case. Subsequently, the exit velocity of water will be approximated in order to calculate an estimated value for gravity throughout the experimental procedure. This report is a continuation of experiment 1. Therefore, the concepts about Mariotte's bottle and the equations involved are presented in the report of experiment 1. As seen in the experiment 1, the behavior h in terms of t is completely linear, meaning that the graph that shows a straight line can be expressed in the following terms. H is equal to bht plus h0. In this equation, h0 represents the initial water level. pH represents the rate of change at which the curve changes. At last, we have the t that represents the independent variable. To calculate the theoretical value for gravity, we will use the following equation. G is equal to 1/2 of the proportion of A out squared times C. This equation is a result of the method of least squares, in which the constant C is equal to pH, the value of the slope of our trend line. While we're talking about microfluidics, we need to explain what they are. Microfluidic devices are those devices that take advantage of the physical and chemical properties of liquid and gases to have a vast variety of applications. Said devices take advantage of the behavior of fluids to guarantee a precise control and manipulation of the fluids in play. These devices have key applications in nanotechnology and biotechnology, as they use complex processes such as the study of cellular processes and the development of nanotechnology. The materials used along the development of the experiment are as listed below. A cylindrical plastic bottle container. Here we used a 3-liter soda bottle. We used an atmospheric tube. In this case, we used a metal straw with a 0.05 diameter, a drain tube. We used a 10 centimeter long antibacterial gel straw with a diameter of 0.05 centimeters, seal to seal the atmospheric tube to the cap of the bottle, and silicone glue. We also used a measuring tape to measure every 2 seconds of the water level dropping. The experiment was developed as follows. First, the water level was measured in delta t of 2 seconds with 5 different values of h. H represents the distance between the inlet tube and the outlet tube. Then we calculated pH, creating a graph line of the data using least squares. Finally, we took the value of the slope of the line b versus t and substituted it in the value for the constant c of the equation. The estimated values for C was that of 2.41 times 10 to the 6th power, and the value for G was that of 0.1517 plus minus 0.13 meters per second square. To calculate the uncertainty of said values, we did 2 separate processes. Having that in mind, C is a coefficient for B in. We considered delta C to be the same value for delta in. Therefore, to calculate the uncertainty of C, we summed the percentile uncertainty of the values T and H. For delta G, we estimated the percentile uncertainties both AH and AIN. Afterwards, the uncertainty product of the sum of the uncertainties for both areas was multiplied by 2, and lastly, the uncertainty for C constant was added to calculate the resultant uncertainty for G. Throughout the experiment, we could clearly see the same behavior in every experiment. It was clearly shown in figures 3 to 8 how well the model adjusts to a linear model. As mentioned in the first part, the exit velocity is supposed to be constant until the lower end of the inlet tube is above water level. This constant decrease in height is shown by the linear feet and its negative rate of change. After doing least squares, the values for b squared were reduced drastically. This could have a great impact on gravity's estimate. After adjusting the v squared over h graph, we noticed a huge discrepancy between the feed line and our experimental values. Afterwards, the constant c was substituted in the gravity's formula, leading us to an estimate for gravity of 0.15 plus minus 0.13 meters per second. After calculating the probable range of our results, we can easily observe that the experimental value is far-fetched from our theoretical value, considering that our probable range is from 0.018 to 0.28 meters per second squared. We can clearly perceive that the theoretical value of 9.81 meters per second squared does not lie within the range of uncertainty. As a result, the estimated values are not conclusive. In addition, the uncertainties for our estimated values were that of 87.68%, meaning that the measurement process was not accurate at all. The goal of this experiment was to calculate the value for gravity. Set gravity obtained was that of 0.15 plus minus 0.13 meters per second. After the development of the experiment, it was concluded that the values found throughout our experimentation were inconclusive, as the expected value did not lie within the probable range of uncertainty. In this experiment, we tried to calculate the value for gravity by measuring the diffusion rate of a Mariotte bottle. After the experimentation, we estimated that the value for gravity was that of 0.15 plus minus 0.13 meters per second squared, with a divergence from the theoretical value of 9.65 meters per second squared, and a probable range of 0.018 to 0.28 meters per second squared, making our results inconclusive.